right, so let's continue now and look at how to get the limit of these rational expressions. So what I'm doing on this problem is I'm varying the degree of the polynomials. These are rational functions. The numerator and the denominator are each polynomials. Okay, so like a polynomial is something like this. If you had a function that was something like 5x squared minus 3x plus 1, happens to be quadratic, but it's a polynomial, and the highest degree exponent is 2, or the highest exponent is 2, that would be the degree of that polynomial. And it winds up telling you some important things. It can be used to give you a sense of the end behavior. It can be used to determine how many zeros at most that function would have. But just remember, degree would be the biggest exponent that you have. So these are rational functions. So they have polynomials on the top and bottom. And so, like here, 3 minus 2x, that's really to the first power. The degree on top is a 1. The degree on the bottom is a 3. Okay. Right here, this looks very similar to what I had before, but the degree on top is a 1, and so is the degree on the bottom. And then on C, the degree on top is an understood 2, the degree on the bottom is a 1. The degree on top is a 2, I should have said, and the degree on the bottom is an understood 1. All right, so that's what I'm varying on these. All right, I'd like to go ahead and take a look at these. And when we do, I'd like to approach it in the very official way of handling this algebraically. So this official way you can handle this is based on this idea that if you wind up having something that turns out to be, say, some fixed number, like, say, a 5, and then the denominator might be an x, but then it winds up that you're looking at the limit as x goes to an infinity of some sort, 5 over a number getting bigger and bigger and bigger is going to equal 0. So the idea is if you have a fixed number on top that might be positive or negative, but some fixed number on top, and in the denominator you have either a positive or a negative infinity, that's going to go to 0. Okay? That's what you utilize. That's what the idea is behind this method and why it works. So if we're trying to look at how to reason this out in an official way, they'll have you do this. Look at the denominator and look at how x is the highest exponent in the denominator is a 3. You got x raised to the third power. So what you could do is come in and wind up dividing everything, top and bottom, by x to the third power. So if I divide the numerator by x to the third, it would get distributed into both of these. And I'm going to do the same thing in the denominator. Divide each of those terms by x to the third. By dividing everywhere by x to the third, what I've written is equivalent to what I had before. Okay. I'm going to take a moment to simplify what I can. So one of the x's will cancel out in that top right spot. X to the third over x to the third will cancel out. And so I'm left with this. So if I plug in numbers going towards positive infinity, then a fixed number over an infinity of some sort is going to go to 0. So that goes to 0, that goes to 0, that goes to 0. So I'm left with 0 on top over a number on the bottom, which is not indeterminate. That turns out to be 0. So that problem has a limit that winds up equaling 0. Okay? All right, so let's use that algebraic process, the official process here. On this one, the highest the degree in the denominator is 1. We have x to the first power is the highest exponent in the denominator, or exponential expression in the denominator. So I'm going to divide by that everywhere. So I'm going to do 3 over x minus 2x over x, and then 3x over x minus 1 over x. Okay? I'm going to simplify. And when I simplify, I wind up with 3 over x minus 2, and then the denominator I have a positive 3 minus 1 over x. Now, here and here, I'm plugging in numbers that are bigger and bigger and bigger, keep going towards positive infinity. And if you have a fixed number over an infinity, then that's going to approach 0. So these two things are going to approach 0, and my limit is going to turn out to be what's left on top divided by what's left on the bottom, negative 2/3. Okay. All right, now when I do that same thing here, the highest power in the denominator is to the first power, so I'm going to divide everywhere by just x. And so I wind up with 3 over x minus 2x squared over x, and then 3x over x minus 1 over x. Do a little simplifying on that. So I have a 3 over x minus a 2x, and then down here, 3 minus 1 over x. Then I'm going to imagine plugging in an infinity, and I know that 3 over an infinity of any kind is going to go to 0. 1 is a fixed number. Even with a negative in front, that's going to go to 0. And so that one I wind up having a negative 2 infinity. And this 2 with an infinity in it, that's going to an infinity, right? So it's like I have a negative infinity on top because of this over a 3 on the bottom. So this is going to wind up being negative infinity when I'm finished. Let me just kind of show that part of it. So it's like this. We have a negative 2 times an infinity over a 3 over a 3, and negative 2 times infinity is still a negative infinity, and dividing by 3 doesn't cancel out the fact that that's still getting more and more negative, so that's going to be just negative infinity. Okay, so when you're doing limits and your x is approaching an infinity of some sort, your answer could turn out to be a 0, it could turn out to be some other fixed number, or it could turn out having an answer that would be infinity when you're finished. Okay? So that is the algebraic process that you typically see described, okay, that tells you how to handle things like that. But we're going to come back to these, and we're going to look at them again a little more informally, okay, in a moment. I want you to make some observations before we do that. So notice here that the degree on the bottom was bigger. So degree on the bottom is bigger. And we wound up getting a limit of 0 for that one. On this one, the degree is the same, top and bottom. And on that one, we wound up getting a number negative 2/3. Okay. And then on this one, the degree was bigger on top. So rather than having, like on this one, rather than having some number, a number that wound up being 0, we wound up having down here, we wound up having a degree bigger on top. We had it winding up approaching an infinity of some sort. Okay? And whether it's positive or negative kind of depends on the original expression. Okay? All right, so let's think a little more about how we might be able to figure these out without going through all this algebraic work. It's really very logical to do it. And behavior on polynomials, when you talk about the end behavior of a polynomial, you focus on the leading term. and you look at the exponent, and that kind of tells you what's going to happen at the ends. That, together with the coefficient out in front, tells you what's going to happen for the end of that polynomial. So we're going to kind of use that idea here, and we're going to think about it that way. We're going to think about how the leading terms are so important. So let's come back to these, and let's revisit this in a more informal way. So in the numerator, this is my leading term. Don't forget to include the negative. In my denominator, this is my leading term. Okay? And so basically, when I'm thinking about the limit of the original function, what I could do is think about doing the limit as x goes to infinity. The limit of the original function would wind up being the same as this, because those leading terms would really wind up overpowering the other stuff you have. Like 3x to the third far overpowers, okay, that little -1. That -1 has really no effect. So we can think about it this way. And then you can imagine your infinity, or think about your infinities going in there. -2, or you could even reduce that first. Let me reduce that first. Okay, so that would wind up being the limit. I'll write it here. The limit as x goes to infinity of -2 over 3x squared. All right. So now, when you think about putting an infinity in there, do you see how you're going to wind up having the denominator growing so much more rapidly than the numerator? Okay. An infinity squared is still an infinity. 3 times that is still an infinity. And you've got just a fixed number over infinity. So that's really going to be 0. Okay? So that's going to wind up equaling 0. Okay? So that's just an informal way that'll wind up giving you the same result that's still very logical, because you're thinking about how, if you're looking for what's happening as x gets bigger and bigger and bigger in either the positive or the negative direction, then the leading term overwhelms what happens, what all the other terms are doing. So you can ignore them and just look at the leading terms. Right? Notice that here, if we did that, here's the leading term of the numerator, here's the leading term of the denominator. So the limit of the original expression would be the same as the limit of this. The effect of this -1 or this 3 is nothing. Okay? And then notice, if I simplified that, that turns out to be the limit as x approaches infinity of just -2/3, a constant. And if you're looking for the limit of a constant, it's going to equal that constant. Notice that -2/3 is the ratio of the leading terms on top and bottom. All right, now let's look at this one. The leading term on top was the -2x squared. On the bottom, it was 3x. So notice how the degree on top being bigger means that the magnitude of the infinity we have on top is more. Or go ahead and simplify before you analyze. Knock out one of those x's and then look at that. See how this one's going to have a numerator that's -2 and then a number getting more and more approaching a positive infinity. -2 times a positive infinity, just think about it like that. -2 times an infinity over 3. That's going to be a negative infinity over 3. Cutting an infinity in 3 pieces, it's still going to be an infinity, and it's a negative over a positive, so that's going to be negative infinity. So a quick and easy way to analyze what the limits at infinity is to really look at leading terms and think about the degree on top and bottom. And these are the cases that you typically have. Okay, and we're going to summarize it on the next page. Okay. All right, now, if you're looking at the limit of a function as x approaches some number, I said it wrong. If you're looking at the limit of a function as x approaches infinity and it equals some fixed number, what that means is maybe the answer turned out to be a 0, or maybe it turned out to be something like -2/3 or 10, okay, but a number. then we would say that the function has a horizontal asymptote at y equals that number. Okay, so previously on these problems, okay, this guy, number 5, you would have a horizontal asymptote at y equals 0. That means if we were to look at the graph of that function, that the ends of that graph would be approaching the x-axis. The x-axis would be a horizontal asymptote. Okay. This one turned out to be a fixed number. That means we're going to have a horizontal asymptote at y equals negative 2/3. That means if we were to graph this function down here at negative 2/3, when we look at the graph, when we're way to the right or way to the left, the graph is going to be approaching that horizontal line. But here we don't have a horizontal asymptote on this one because the limit didn't turn out to be a fixed number. So this one has no horizontal asymptote. Remember back in Math 112, part of your job was to find horizontal asymptotes if they existed. And here's the rule that you used back in Math 112. Okay. All right, so if we had a rational function, that means we've got, let me see which one's going to be which. Okay, so if n is the degree of the numerator, what it means is you got a rational function, and it might be something like, 2x to the 5th plus 3x to the 4th plus. It can have a whole bunch of terms in it. And then down here you have something else, x to a power, and then maybe a bunch of other terms. And okay, this right here is saying you've got to look at, let me just use an n and not put actual things in there. So this says you got to look at these. So n is the degree of the numerator, meaning it's the exponent with it's the term with the biggest exponent. M is the exponent for the term with the biggest one. So it's the highest exponent. All right, so think about that. And this one is saying if the numerator, the degree of the numerator is smaller. Okay, so the degree on the bottom is bigger. I'm going to write it over here. So it's bigger on the bottom. Okay, this case is if the degree is the same, top and bottom. And then this case is saying the degree is bigger on top. Okay. All right, so we know if the degree were bigger on top, that the limit really is not going to exist. It'll go towards an infinity, either a positive or a negative infinity. You're not going to have a horizontal asymptote. You're going to have a slant asymptote. Maybe it's going to look like that or that. If it's the degree is 1 bigger on top, it'll be a line, and it'll do one of those. If it's a degree that's 2 bigger on top, then your function's going to approach a parabola that might look like that, or it might look like that. But in the long run, it's going to approach that. If it's 3 bigger, you don't have a horizontal asymptote. Your graph is going to approach a cubic of function one way or the other. Okay. The main thing is it won't have any horizontal asymptotes. Okay. Case 2 is saying if you have something like what did we have on the previous one? I'll use that as an example. If you had a negative 2x was your leading term on top, and then a 3x was your leading term on the bottom, then you know you're going to have a horizontal asymptote equal to the ratio of those leading terms. So in that case, it would be y equals negative 2/3. Okay. And then this one is like our first problem. if the degree is bigger on the bottom. So if your leading term was like a negative 2x, and then there's other stuff potentially there, and the leading term on the bottom was a 3x to the third, bigger degree on the bottom means, see how it's going to be growing much more rapidly than what's on top, then this whole thing is going to wind up approaching 0. So you'll have a horizontal asymptote at y equals 0. Okay? Always. So you really can just compare the degree to determine that.